It seems to be a favourite of chemistry teachers to have you draw atoms in terms of a thing called a Lewis diagram. Now we're going to bump into Mr. Lewis in various topics. We start off with him in the atom and the Lewis diagrams, and then we come back to see him, of course, in acids and bases when we talk about his theory of what makes up an acid and base. So a Lewis diagram is going to be all about showing electrons. On the front, I've shown you what actually happens, or what a little animation or a little picture of ionic structures. And we're going to be talking about ionic structures as well as forming just atoms and sharing electrons and goodness knows what. We've already spent time talking about the packing of electrons in atoms. But when we're showing them, especially the more complex atoms, it's very, very important that we don't get mixed up. So what we should do is to show only the valence electrons, because they're more likely or most likely to be the ones involved in the reactions and in the changes that occur as we go through this. Now, so we're going to look at the three different types of things that are going on. We're going to look at how we show atoms, how we show ions, and how we show molecules. And as we can see, or as we will see, there are various ways we can do this, or combinations of ways. All are acceptable, and this is often tested in paper 1, where they will give you the diagram and ask you the correct one, or paper 2, where you'll be asked to draw a Lewis diagram of a molecule, most likely a molecule. Right. Probably the most obvious way for us to show electrons, valence electrons, are to show them as dots or crosses. Now, for the sake of us doing it, I'm going to show them as little balls, and they're going to go here. Now, I'm going to use the atom fluorine, and as we know, fluorine has the electron packing of 2.7. In other words, 7 electrons in its valence shell. So let's see how they could pattern in. We could have them equally spaced around, but I'm going to suggest to you to do it this way. I'm going to suggest to you that you start to think about putting them in pairs, because when we do around an atom, we tend to find that pairs of electrons tend to be very useful for us to consider. Now, I'm having trouble with these electrons. So I've got 4 in there at the moment. There's number 5, number 6, and there's number 7. So if we're working on the octet rule, we know that fluorine would love to have an extra electron so it could fill it up and form a fluoride ion. And this in real terms is what it does. And so in natural terms, fluorine will try to gain that extra electron and form this. So that would be one way we could show a fluorine atom. Now, an alternative way of showing these electrons, and instead of having to do 2 dots for a pair, we use a line. Now, the line signifies a pair of electrons, so please don't show 7 pairs of electrons around fluorine. So if we're considering fluorine, we would do something like this. There is 1 pair, there is a second pair, there, and there is a third pair. They almost form a box-like structure around fluorine. So there are 6 electrons there at the moment. Now, to show the 7th, I can't do half a line. I must use something else. So if I use a combination of these things, I can see that I've used my balls again to show each single electron and lines to show pairs. So a fluorine atom could also be shown in this way. This is perfectly acceptable to see a combination of lines and crosses, dots, balls used to show electrons. This is a very, very helpful hint for when you are doing molecules and compounds later on. Now, of course, we have to show things as they really are. We have electrons involved in bonding and electrons not involved in bonding as part of what's going on. Now, we know that the line before showed pairs, and we know that a single bond in a molecule involves a pair of electrons. So why not use that to help us out? All right, so if we're doing a simple molecule like hydrogen fluoride, now we know that hydrogen has one electron, so its one electron will be used in bonding. Fluorine has 7, so one will be shown in bonding, one will be used in bonding, and the other 6 will be shown around the outside in normal pairs. In this case, I'm going to show it in form of the line structure. So let's put the bond in first. So there's my bond between, and I've got a pair of electrons involved in that. Now let's put the other pairs in there. So I can put a pair up here. Now unfortunately, I've done lines too big, but that's okay. I'll put another pair here and the third pair there. So we can see I've got 6 unbonded electrons next to the fluorine atom. Got 6 unbonded electrons next to the fluorine atom. Some are here. I'll just point them out to you. Right, we've got them over here, there, 1, 2 there, 2 there, 2 there. 1 of fluorine's electrons there, 1 of hydrogen's there. So fluorine now has access to 8 electrons, so it's happy. Hydrogen's got access to 2 electrons, it's happy, and life goes on. We've also seen how atoms can gain or lose electrons to form ions. So do we use Lewis diagrams for that? We sure do. And in general trends, we show metal ions with empty shells because they've lost electrons. So we show the valence shell as empty. So in the case of sodium down here, we show nothing around it. There are no electrons at all. But if we're showing what's going on, we must show it's an ion, and we do that by using square brackets. If I've got square brackets around my Lewis diagram, it tells me I have an ion. But the last thing I need to show is the fact that the ion will have a charge, and we know that the sodium ion has a charge of 1+. So that would be a Lewis diagram. What we can see here would be a Lewis diagram for a sodium ion. Not that hard. Obviously, if we're doing a non-metal, then we would have a full set of, in most cases, it would be 8 electrons around it, and the charge outside the brackets as well. So it'd be a negative charge, and the charge would correspond to how many electrons I have added. So let's see if it works for the fluoride ion. So the fluoride ion is going to have, fluorine atom had 7 electrons, so to fill up the octet we need to add 1 more electron to it. So that means we're going to have 4 pairs of electrons, so let's put them in. One pair there, 1 pair there, 1 pair there, 1 pair there. So now the fluoride ion has formed, so we've got to show it. So we add the square bracket, and I've used colour for adding square brackets. Of course, you don't have to do that. And since we've added 1 electron, it must have a negative charge. So I would show the fluoride ion as that, and that would be my Lewis diagram for it. Right, so we've seen atoms, we've seen ions. Now let's look at what goes on in terms of our molecules. And what I've done is I've put 2 molecules here, and I've started them, but I haven't finished them. And so in the next bit, I'm just going to finish them for us and show us how we could show these as Lewis diagrams. All right, I've got a fluorine molecule, F2, and I've got an oxygen molecule. Now, fluorine has a single bond between the 2 atoms. I know this because each atom requires 1 electron. So that means they've got to give the number of electrons we require means the number of bonds you have to form or number of electrons you have to share. So let's give our fluorine molecule its bond. But that's not a Lewis diagram, because a Lewis diagram shows all of the electrons around all of the atoms. At the moment, I'm only showing 2 electrons. So let's show the rest around this fluorine atom. There you are. There's 1 pair, 2 pairs, and there's the 3rd pair. I'm just going to fix these up a little bit so it's a little bit tidier. Right, so you form the little boxes around fluorine, and the same for the other side. There's 1, there's 2, and there's the 3rd pair. So now I've shown what the molecule of fluorine looks like. If I change it down to oxygen, I see oxygen has 6 electrons in its valence shell, so it needs 2 to fill up. Now, to share the electrons it needs to share the same number it needs. So each oxygen atom must share 2 electrons. So that means I'm going to have a grand total of 4 electrons shared. Now, if each pair of shared electrons corresponds to a bond, then I'm going to have a double bond here between these 2 atoms. So there's 1 pair of electrons, there's the other pair of electrons. So we have an O double bond. Now then I'm going to show these other electrons we have, the other pairs. So that means I've got, oxygen had 6, I've got 1, that one's 1 from there here, 1 from there here, so there's its 2 it's shared, that one to that one, that one to that one, there's its 2 it's shared. It had 6 to start off with, so I've got to show 4 more electrons. So let's use the lines again. So I'm going to show them like this. Now, the reason I do this is because all these pairs of electrons, what are they going to do to each other? Electrostatics tell us they're going to push away from each other. So we end up with a little bit of a shape, and I like showing it to let me think about what sort of shape my molecule might be. So then if I've done it for one atom, now let's do the other atom. Get these things down to work. There we'll have a mirror image across the other side. And so we end up with showing 3 lines. Now don't be tricked with this one. These lines are much too big really, but they show out well. So we can see how the atoms are, or the electrons are arranged around each one of these atoms in a molecule. I hope that makes some sense. And all we do when we transfer it to a larger molecule is we do the same thing and think about how many electrons we need to have fitting.